Welcome to solverfy.
First, let's build the molecular orbital of an alkene from two p orbitals. Each p orbital is a dumbbell shape with the positive sign of the wave function on one side of the double bond and the negative sign on the opposite side. Each carbon contributes one orbital to the system, one p orbital. So the number of molecular orbitals would be 2. It must match the number of initial p orbitals. So now we have 2 molecular orbitals. P orbitals are contributing to each molecular orbital with coefficients of the same sign, plus, plus, or opposite signs, plus, minus. Those coefficients, they match the most for the lowest in energy orbital, and they mismatch more and more as the energy goes up. As a consequence, the lowest in energy orbital is symmetric with respect to the plane of symmetry, and the next orbital is antisymmetric with respect to the plane of symmetry. Now let's build the molecular orbital of a conjugated diene. Now we have 4 initial p orbitals, one from each of 4 carbons of the system. For each molecular orbital, p orbitals are contributing with same signs of coefficients. Or opposite signs. The signs are perfectly matching for the lowest in energy orbital, and their mismatch increases more and more as the energy goes up. This makes the lowest in energy orbital symmetric with respect to the plane of symmetry. Next one antisymmetric. Next one is symmetric. Next one is antisymmetric. Now let's populate our orbitals with electrons. For alkene, there are 2 electrons, one from each carbon at the double bond, and those 2 electrons are sitting on the lowest in energy orbital. For diene, there are 4 electrons, one from each carbon, and they are sitting on 2 lowest in energy orbitals. Now let's pick the orbitals of interest. We need the HOMO of alkene. HOMO stands for highest occupied molecular orbital, which is this one, and it's symmetric. For diene, we need LUMO, which is lowest unoccupied molecular orbital. It's this one. And it's also symmetric. So the symmetry matches. Now let's put together HOMO of alkene and LUMO of the diene. HOMO of alkene and LUMO of diene. Now, let's show the signs of wave functions, which must be opposite on the opposite side of the plane. When we put together two orbitals in the superfacial fashion or by same faces, those signs of wave functions perfectly match, plus to plus, minus to minus. It makes the orbitals on the path of addition to have the lowest energy, and it makes the addition chemically favorable. This happens because the symmetry types of HOMO of alkene and LUMO of diene match, both are symmetric. Therefore, the suprafacial addition is symmetry allowed. Often, the addition requires heat and also can be called thermal addition.